This example talk about the communication system in which whenever the transmission takes place with the digits 0 and 1 in the several stages. Now, we are going to define the random variable x naught be the digit transmitted initially, that is a 0th step. Either the transmission digit will be 0 or 1, therefore, only two possibilities can be takes place at any nth step transmission, either 0 or 1. Like that, we are making the transmission over the different stages. Therefore, this xn over the n will form a stochastic process, because you never know which digit is transmitted in the nth stage. So, each stage is going to be a one random variable and you have a collection of random variable over the stages. Therefore, it is a sequence of random variables. So, this is going to form a stochastic process, and this stochastic process is nothing but the discrete time, discrete state stochastic process, because the possible values of xn is going to be 0 or 1. Therefore, the state space is 0 or 1, and it is a discrete time, discrete state stochastic process. The way the subsequent transmission takes place depends only on the last transmission, not the previous stages. Therefore, you can assume that this follows a Markov property. Therefore, this stochastic process is going to be called it as a discrete time Markov chain. Now, our interest is to find out. So, now I will provide what is the one step transition probability for the Markov chain, or let me give the transition diagram for that. So, state transition diagram, the possible states are 0 or 1 because the state space is 0 and 1, and the probability that in the next step also the transmission is 0 with the probability 1 minus a. This is a conditional probability. This is the conditional probability of the nth stage the transmission was 0. The n plus 1th stage is also the transmission is 0 with the probability 1 minus a. The one step transition probability of system is moving from 0 to 1, that probability is a. That means, the nth stage the transmission was digit 0, the n plus 1th stage also the n plus 1th stage the transmission will be the digit 1 with the probability a. Similarly, I am going to supply the one step transition probability of 1 to 1, that is 1 minus b, and this is b. That means, this 1 to 0, that probability is 1 to 0 is b, and 1 to 1 is 1 minus b. Obviously, this a is lies between 0 to 1 and b is also lies between 1. So, this is the a is the probability that the system is transmitting from the 0th step nth stage with the digit 0 and the n plus 1th stage with the probability with the stage with the digit 1, that probability is a. Therefore, the negation is 1 minus a, because the system can transmit either 0 or 1. So, once you say that the one step transition probability of 0 to 1 is a, then 0 to 0 will be 1 minus a. Similarly, 1 to 0 is given as the probability b, and the other digit transmission will be 1. Therefore, it is going to be 1 to 1 will be 1 minus b. So, this is the state transition diagram, and this is the one step transition probability for a given time homogeneous discrete time Markov chain. Our interest is to find out what is the distribution of xn for n. For that, you need what is the n step transition probability matrix. Since the one step transition probability matrix is given, you can find out p square, p power 3 and so on. By induction method, you can find out the p power m, but using the p power m, you can find out the p m plus n. Therefore, you can come to the conclusion what is the n step transition probability of system is moving from 0 to 1 and to 0 to 0 and so on. So, this is nothing but I am just giving the only the result b plus a times 1 minus a minus b power n divided by a plus b, and this is nothing but a minus a times 1 minus a minus b power n divided by a plus b. Similarly, if we find out the n step transition probability of system moving from 1 to 0, that is b minus b times 1 minus a minus b power n divided by a plus b, and this is nothing but a plus b times 1 minus a minus b power n divided by a plus b. So, here I am just giving the n step transition probability in matrix form. By given p, you should find out the p square p power cube. By induction you can find out the p power n, and this is valid provided 1 minus a minus b which is less than 1, because you are finding the p power n matrix. So, here it needs some determinant also, unless otherwise the absolute of 1 minus a minus b which is less than 1, this result is not valid. So, provided this condition, the p of n, that is the matrix. So, that is same as p power n also. P of n is same as p power n. So, as n tends to infinity, you can come to the conclusion what is the probability that the system will be in the state 0, that is same as b divided by a plus b, and similarly what is the probability that the system will be in the state 1 as n tends to infinity, that will be a divided by a plus b. This can be visualized from the state transition diagram easily. Whenever the system is keep moving into the state 0 or 1 with the probability a, b, and with the self loop 1 minus a and 1 minus b, the subsequent stages the system will be in any one of these two states. So, with the proportion of b divided by a plus b, the system will be in the state 1. Similarly, with the proportion a divided by a plus b, the system will be in the state 1. With the proportion b divided by a plus b, the system will be in the state 0 in a longer run. The interpretation of as n tends to infinity, this probability is nothing but in a long run with this proportion, the system will be in the state 0 or 1. So, this state transition diagram will be useful to study the long run distribution, or where the system will be as n tends to infinity. To study those things, the state transition diagram will be useful. Now, we will move into the next problem, that is example 4. Let the sequence of random variable be a sequence of independent random variables. With condition, the probability of yn takes a value 1, that probability is p, that is same as 1 minus the probability of yn takes a value minus 1. We have a stochastic process, and each random variable is a independent random variable, and the probability mass function is provided with this situation. The probability of yn takes a value 1 is p. You can assume that the p takes a value 0 to 1. that is same as 1 minus of probability of yn takes a value minus 1 for all n. Now, I am going to define another random variable. Let xn be defined by x naught is equal to 0, whereas x n plus 1 onwards, that is going to be x n plus y n plus 1 for n is equal to 1, 2 and so on. So, we are defining another random variable x n with the x naught is equal to 0 and x n plus 1 is equal to x n plus y n plus 1. Now, the question is, check x n, that stochastic process is the DTMC. If it is a DTMC, also find out what is the probability of x n takes a value k. We started with one stochastic process and we define another stochastic process with the earlier stochastic process, and check whether the given the new stochastic process is a discrete time Markov chain, that is a default one, that is a time homogeneous discrete time Markov chain. If so, then what is the probability of x n takes a value k? That is nothing but find out the distribution of x n. So, how to find out this? The given or the x n is going to be the DTMC. Since y n takes a value 1 with the probability p and y n takes a value minus 1 with the probability 1 minus p, you can make out the possible values of y n is going to be 0 or plus or minus 1, plus or minus 2 and so on, because the relation is x naught is equal to 0 and x n is x n plus y n plus 1, and the range of y n is 1 comma minus 1. Therefore, the range of x n, that will form a state space and x naught is equal to 0. Therefore, x n, that relation is x n plus 1, x n plus 1 is equal to x n plus y n plus 1. So, n takes a value 1 and so on. Therefore, the possible values of x n will be 0, plus or minus 1 or plus or minus 2 and so on. Therefore, that will form a state space. Now, the given clue is probability of y n takes a value 1 is probability p, and the probability of y n takes a value minus 1, that is 1 minus p, and the probability p is lies between 0 to 1. So, using this information, you can make a state space of the y n, that is going to be 1, 2 and so on, minus 1, minus 2 and so on. Now, we can fill up what is the one step transition of system is moving from 0 to 1. That means the x 1 0 to 1, suppose you substitute 0 here, then suppose it takes a value 1, then the system can move from the state 0 to 1 in one step. Suppose you put the value x naught x n is equal to 0, suppose you put x n is equal to 0 and y n plus 1 takes a value 1 with the probability p, then the x n plus 1 value will be 1 with the probability p. Correct. Now, we can go for what is the state transition probability of 1 to 0. Suppose x n value was 1, suppose y n plus 1 value was minus 1, then the x n plus 1 value will be 0. So, the one step transition of a system moving from 1 to 0 because of happening probability of y n plus 1 is equal to minus 1, that probability is 1 minus p. So, this is going to be. So, whenever the system is moving from one step forward, that probability will be the probability p, and one step backward, that probability will be 1 minus p. So, this is the way it goes forward step, and this is the way it goes to the backward step. So, you can fill up all other probabilities, forward probability with the probability p and the backward probability with the 1 minus p. Also, we can come to the conclusion, the way we have written x n plus 1 is equal to x n plus y n plus 1, and all the y i's are independent random variable. The x n plus 1 going to take the value depends only on x n, not the previous x n minus 1 or x n minus 2 and so on. Therefore, the conditional distribution of x n plus 1 given that x n minus 1 till x naught, that is same as the conditional distribution of x n plus 1 given x n. That means, the x n is going to satisfy the Markov property because of this relation, because of x n plus 1 is equal to x n plus independent random variable. Therefore, the x n is equal to 1, 2, 3 and so on. This stochastic process is going to satisfy the Markov property. Therefore, this discrete time discrete state stochastic process is going to be the discrete time Markov chain because of the Markov properties satisfied. Once it is Markov property satisfied, by using the Chapman-Kolmogorov equation, you can find out what is the distribution of x n takes the value k. That is nothing but where it started at time 0 and what is the conditional distribution of n step transition probability, and the n step transition probability is nothing but the element from the p power n, and from here you can find out the one step transition probability matrix. From the one step transition probability matrix you can find out the p square, p cube and so on, and you can find out the p power n, and that element is going to be the n step transition probability. Using that you can find out the distribution, and since we do not know the value of p, where p is lies between 0 to 1, it is I am not going to discuss the computational aspect of finding out the distribution. This is left as an exercise and the final answer is provided. The difference between the earlier example and this example, the state space is going to be a countably infinite. Therefore, the P is not going to be a easy matrix, it is going to be a matrix with the many elements in it. Therefore, finding out the P square and the P power n, it is going to be little complicated than the usual square matrix. So, hence the conclusion is by knowing the initial probability vector and the one step transition probability matrix or the state transition diagram, we can get the distribution of x n for any n. There is a small mistake, the running index for x n plus 1 value is equal to x n plus y n plus 1, that is starting from 0, 1, 2, and similarly the previous slide x n plus 1 is equal to x n plus y n plus 1, and n is running from 0, 1, 2 and so on. So, in this lecture we have discussed Chapman-Kolmogorov equation, and also we have discussed the n step transition probability matrix. So, the n step transition probability matrix can be computed from the one step transition probability matrix with the power of that n, and also we have discussed 4 simple examples for explaining the Chapman-Kolmogorov equation and the n-step transition probability matrix. For the lecture 1 and 2, we have used these 3 books for as a reference. The first one is J. Mehdi's Stochastic Processes book, and the second one is Kishore Trivedi Probability and Statistics with the Reliability, Queuing and Computer Science Applications. The third one is Shelton Ross Introduction to Probability Models. So with this I complete the lecture 2 of discrete time Markov chain. Thanks.